Now in this Prestressed beam lecture, we will see the elastic analysis due to flexure. That means we will get to know that how we can calculate the amount of stress in topmost fiber and bottommost fiber of a pre-stressed beam. We will be analyzing the beam sections for this lecture in this lecture. So starting with the concentric tendon. Concentric tendon means the tendon simply goes through the center line. It merges with the center line. There is no eccentricity. In general cases, we used to place the tendon in downward of this a little bit downward from this center line, but if it is concentric, that means if it merges with the center line, then what will happen? Let's see what is going to be the total formula to calculate the stresses or to analyze the stresses. So due to this applying of compressive forces through this tendon, what will happen? The tendon will tend to go back to its original shape or original state. So compressive force F will be applied in this beam, and due to this compressive force F, the stress, which is compressive stress will be simply force divided by its cross-sectional area. Considering the cross-sectional area as A, so the compressive stress will be force F divided by area. Why is it negative? Because we are applying compressive force. So now we are done with the pre-stressing. Then after that, when it will be subjected to working load or service loads, what will happen? It will bend in this pattern. It will go through this pattern of bending. So in this pattern of bending, due to the service load, we will be able to see compression in the topmost fiber, which is indicated by negative, and tension in the down fiber, which is generally indicated by positive. We have already known in structure 3 that in order to calculate this bending stress in any of the fibers, the formula is simply my by I. M is the moment which is created due to the service loads. Y is the depth of the beam from the center line. That means the distance of topmost fiber or bottommost fiber from the center line or from the centroid of the section. So we can see the section here. So in this case, the value of Y will be simply the distance from center line to the topmost fiber or bottommost fiber, whatever we may ask to calculate. So, and the last one, which is I is simply the moment of inertia. For a rectangular section, the moment of inertia I is equals to bh cube over 12 bh cube by 12 where b is the width of the section and h is the total height of the section. Okay, so we are getting the bending stress due to the moment that was created due to service loads from using this formula, which is my by I. We are using positive and negative signs both in our formula because we know positive stress or tensile stress will be created in bottom fiber and compressive stress or negative stress will be created at topmost fiber in case of external loadings. So this is the compressive stress due to tensioning, pretensioning, and this is the compressive stress due to bending. So in total, in case of concentric tendon, where the tendon passes through the center line, the total stress will be minus F by A plus minus my by I. We are simply summing up these two things and we'll getting the total stress here. Now, if the tendon is not concentric, or if we are considering it as eccentric one, that means a bit lower from the center, if it passes through this point like the next one, if here this is the center line but the tendon has passed through the downward portion a bit down from the center of gravity or CG or the center line. So considering the distance from center line is E, so E will be the eccentricity, and for this eccentricity an extra term will be added or summed up in the previous formula that we have got from here. So an extra term will come, so this extra term will be Fey by I. We know the bending formula of bending stress is my by I, my over I, but in this case where we can see the eccentricity, due to this eccentricity, while we are applying compressive force in the section, what will happen, it will try to bend in this pattern. That means the opposite one of the service loadings one, opposite of the service loading one. So in this type of bending pattern we will be able to see tension in the upward portion and compression in the downward portion. That means tension in the topmost fiber or positive stress in the topmost fiber and negative stress at the downmost or bottom fiber of the beam. So for this type of bending, that means moment will be created, and this moment M is simply the force we are applying, the compressive force F we are applying, and distance. We know moment is equals to force into distance, and here the distance will be simply the eccentricity, so F into E. So in total the formula will be Fey by I. So this is our formula that is being added in the total formula. So this term will be added in this formula. So Fey by I, plugging the value of M here, Fey by over I. So we are getting it here why the plus minus sign has been used before the Fey over I portion. We can see from this section that due to the pre-stressing of a eccentric tendon, tension will occur in the upward or topmost fiber and compression in the bottommost fiber. So as both positive and negative stresses will come, so we are using positive and negative sign in our formula, and this one my by I is simply like the previous one we have told. That means due to the external loading which came, due to the external loading we know that this will come. That means compression in topmost fiber and tension in bottom fiber. So and this F over I are simply due to compressive force. So we can see here this extra term, and our total formula will be this one, this total one, minus F by A plus minus Fey over I plus minus my over I. Okay, here M is the moment. This moment will, and as this my by over I is the portion that has arise from the external loading, so this M will be the moment which will be created due to external loading, and this F is the compressive force that is applied through the tendons, E is the eccentricity, Y is the distance from the center to the topmost fiber or bottommost fiber, whichever we will be considering to calculate the stresses, and I is the moment of inertia, and A is the cross-sectional area, that means area of this cross section. So Let's see example 1. Here we can see an eccentric tendon. The eccentricity value is given as 6 inch. The cross-sectional area is given as 20 into 30, and now the pre-stress is given as 360 kip. That means the compressive force that is going to be applied here is 360 kip. Now we can also see here the external loading as 3 kip per feet. 3 kip per feet. So firstly, we can write the full formula to calculate the stresses. So which is F by A plus minus Fe y by I plus minus My by I. Now the compressive force F is equals to 360 kip. It's given in the question. That means kilopound, 360 kilopound. So converting it into pound, we will get 360,000 pound. Eccentricity is given as 6 inch, and y, this y we know that simply it is distance from center to the topmost fiber or bottommost fiber. So in this case it is the uniform one. That means this is a rectangular section. So for rectangular section, it is y is simply the half of the section's depth. So the total depth is 30, then y will be 15. That means distance from center to the topmost fiber or distance from center to the bottommost fiber. So half of 30 is 15. So we are plugging here y is equals to 15. The area will be 600 inches square, cross-sectional area. Now the moment of inertia I is bh cube by 12 for a rectangular section. So bh cube by 12 I. So we are getting the value of I here. Now moment due to this uniformly distributed load. We know that moment due to uniformly distributed load, if we draw the shear force and bending moment diagram, as in this question we are asked to determine the top and bottom fiber stresses. That means stress at top fiber of this beam section and bottom fiber of this beam section, stresses at mid section. So we are asked to calculate the moment at mid section. We know that due to uniformly distributed load, maximum moment arises in the mid section, and the value of maximum moment is WL squared by 8. You can see here the formula WL squared by 8, where W is the uniformly distributed load in per feet or per inch or per unit length. So we are plugging the value of W as 3. It's given as 3 kip per feet. That's why we are plugging so. Then L is given as the length, 24 feet. 24 feet. We are plugging the value of L and 8. From here we will get the moment as 216 kip feet. So if we want to convert it into pound, then we can, it is kip feet. Kip means kilopound. So for converting it into pound and into inch, we will need to multiply with 12 and 1000. That means in total to 12,000. So we will get the value as 2592340 pound inch. So we have got all the values. Now we'll be plugging those values here in the formula. Now we will get something like this one. Minus 600 plus minus 720 for this term, plus minus 720, and for this term 864 plus minus 864. So now while we are asked to calculate the top fiber stresses, that means we have already known earlier that in case of top fiber, due to eccentric, in case of pre-stressing, we can see tension in the top fiber. That means positive stress in the top fiber. So as this term which is Fey by I arises for the pre-stressing, so we will be using the positive value of this one, which is plus 720 in case of top fiber. So why are we using plus 720? It is because this term 720 has arise or has been calculated for using from this term, which is FEY by I. This term is from the theory we have learned that this term arises from the pre-stressing or pre-stressing of eccentric beams. So in case of pre-stressing, tension develops in the topmost fiber. Tension develops, that means positive stress develops. So as tension develops, so for topmost fiber, we know for pre-stressing tension develops, so plus 720 has been used. We also know that in case of external loading stresses of beams, bending stresses of beams due to external loading, compression develops in topmost fiber, so negative stress. So as compression develops in topmost fiber, so we are using negative 864, and this is will always be minus, as we can see from the calculation, minus 600. So from here we'll get the topmost fiber stress. Similarly, for bottom fiber, this will be fixed, we know, and we can get plus minus 720, as we know that for bottom fiber, for pre-stressing cases, in pre-stressing cases, compression develops or compressive stress develops, which is negative. So for bottom fiber, we are using -1, negative value, and finally the last one, which is due to external loading. In case of external loading, bending stresses is positive in bottom fiber, which is tension, as tension will occur in bottom fiber due to external loadings, and this term has came from external loading stress due to external loading. So as we know that due to external loading, tension will occur in bottom fiber, so tension is positive, so we are using here positive. So from here we will get the value of bottom fiber stress also. Now we will conclude that the stress at top fiber is minus 744 psi and bottom fiber is minus 456 psi. So we can draw this figure also. That means this was uniform for the compressive force minus F by A. This has came for pre-stressing, which is positive or tension in top fiber and compression in bottom fiber. It's a uniform one, and the opposite one, which is for external loading, bending stress due to external loading, there will be compression in top fiber and tension in bottom fiber. So you will get the resultant as top fiber, our value is minus 744, and in bottom fiber it's minus 456. So we are putting those two values at one side of the line, this one side of this vertical line, as both are negative and 744 is greater. So we are plugging it here and 456, and we are drawing this figure, final figure. So we need to conclude in this way. Example 2 and 3 are almost same, exactly same. The differences is these two are mainly much easier than the first one. So the differences is, in example 2 we are asked to calculate top and bottom fiber stresses at support of the pre-stress beam, and in previous example we were asked to calculate it at midsection. For midsection, the formula of moment is WL square by 8 for a uniform distributed load, and as in example 2 we are asked to calculate the bottom fiber and top fiber stresses at support. That means we need to calculate the moment at support first, but we know that at support the moment will always be 0. So as the moment is 0, simply we'll plug the value of moment m0 here, then this term will be 0. So this term will be 0, others will remain same as the values are same, so others will remain same. And for top fiber stresses we will take positive, as we know that in case of top fiber. In case of pre-stressing, at top fiber positive stresses develops, so plus 720. We can see here plus 720. So in top fiber plus 720, and for pre-stressing compression develops at bottom fiber, so minus 720 for bottom, minus 720 for bottom. And in this way we will conclude the result and draw the final figure as well. You can see at top fiber it's plus 120 psi, and at bottom fiber it's minus 1320. So plus 120 and minus 1320, and we are joining the lines. This is our final figure. And in example 3, exactly same calculation, but the difference is in this example we are asked to calculate the pre-stressing wear concentric. That means the wear pre-stressing wear is concentric. That means the wear passes through the center line. That means here the value of E is equals to simply 0, as there is no eccentricity. That means it is concentric. So as the value of E will be 0, so this term will be 0. So this term will be 0 and others will remain same. In this case we know that for external loading this term has came. So for external loading, compression develops at top fiber. We can see the value plus minus 864 compression at top fiber and tension at bottom fiber. So for top fiber we are using minus 864, and for bottom fiber we are using plus 864, and we are concluding the result as well. So these three are the examples or problems regarding pre-stressing beam. Thank you.